Hi there, this is Magnetism lesson 3, and in this one we're going to do flux and flux linkage. Let's start with this recap question from lesson 2. If you want to pause and have a go. The path followed by an electron of momentum P carrying charge negative E, which enters a magnetic field at right angles, is a circular arc of radius r. What would be the radius of the circular arc followed by an alpha particle, which has momentum 2p, carrying a charge plus 2e, which entered the same field at right angles? So the original radius is r, and we're going to see how this changes, if it does. So BQV equals mv squared over r. V's cancel, and radius of curvature is mv over bq. And mv is obviously momentum. So the radius is momentum divided by bq. So the momentum is doubled, so I need to double the momentum, and the charge is also doubled. So the radius of curvature is the same. So the answer is just r. So it's the same as it was originally. You could make a note that it's in the opposite direction. If, however, you wrote minus r, that would be okay. So let's move on. Hopefully that's all right. Here's another question. If you want to pause and have a go at this one, then I'll take you through the answer. Below is an arrangement for determining the masses of ions. Positive ions pass through P, this point, and enter a uniform magnetic field. The ions experience a force and travel in a semicircular path of diameter d. So the first one, what direction is the magnetic field set up in? So if you use your left-hand rule, the ion source, the positive ions, so positive to negative, so as it's entering point P, if your second finger should be pointing in this direction. So your second finger should be pointing in that direction. The force that's experienced is pushing in this direction, so your thumb should be in that direction. So with your second finger and your thumb pointing in those directions, your first finger should be pointing into the page. So the direction, what is the direction is the magnetic field set up in? Into page, or into the screen, or into the plane of the diagram. Question 2, explain why ions travel in a semicircular path as shown in the diagram. So I'm just going to write this out. So a charged particle in a magnetic field, I'm just going to put mag field, experiences a force. And that force is always at a right angle to its motion. So full stop. Right angle to its motion. Which means it will exhibit circular motion, as it does in this case in this diagram. So initially a force will be in that direction, and then as it changes direction, the force will continue to be applied at a right angle to its motion, which will force it to exhibit circular motion. 3, derive an equation, so the diameter of the path as shown in the diagram. So same as from earlier, so BQV equals mv squared over r, cancel the v's, rearrange to get r, so r is again mv over bq. And the radius is obviously half the diameter, so d over 2. So if we sub in d over 2 for radius, you get d over 2 equals mv over bq, and then rearrange to get d by times in by 2. So the diameter would be 2mv over bq. That's the equation. And then we're going to use that to answer question 4. So we want charge to mass ratio, so that means charge divided by mass. So we need to rearrange this to get charge over mass. So charge over mass will be equal to 2V over BD. Then we just need to put these numbers in. So we've got 2 times V. So that'll be 2 times the velocity, 7.2, times 10 to the power 4, divided by B, which is 0.38. Multiplied by the diameter, 105 times 10 to the minus 3. And that gives us an answer of 3.61. It's times 10 to the 6. So I have to write it like this because there's not much room. Coulombs per kilogram. Like this one. Hopefully that went okay. Let's move on. Here's a simple bar magnet with an illustration of what the magnetic field might look like around it. You'll notice that none of the field lines touch each other and that they all go from north to south. So the density of the field lines indicates the strength of the field in that certain position. So comparatively, we've got a weak field, and at the poles of the magnet, obviously a stronger field. As you can see, there's more flux or more field lines in that region. So it has a greater flux density or magnetic field strength. So magnetic flux. So the equation for flux, so that's symbol phi, is equal to B times A. So magnetic flux density multiplied by the area. So flux is measured in Weber. Area is measured in meters squared. Magnetic flux density or field strength is typically measured in Tesla. Or, we've done this before, Weber per meter squared. Either or. And what we're doing, we're always looking for the component that's perpendicular. So if it was an angle, it would be this component. So the value for the flux in this situation, on this diagram at the bottom, will be to BA multiplied by, then you have to choose between sine and cos. Now this one is opposite the angle. So that would be sine theta. So we need to be careful with these. You'll see in a couple of examples in this lesson. So let's move on. Simple question. So let's pause and have a go. A single coil in a region of space has a magnetic flux density or field strength of 0.6 Tesla and a cross-sectional area of 200 millimeters squared. Calculate the flux. So let's do that now. So we've got to be careful with the 200 millimeters squared. So just a quick recap. So that'll be 200. The easiest way to do these is millimeters. So that'll be times 10 to the minus 3. And then the squared, just do the same again. So we're going to times by 10 to the minus 3 again. So that will give us 200 times 10 to the minus 6 meters squared. So let's do this. So flux is equal to BA. So that'll be 0.6 multiplied by the area, which is 200 millimeters squared. So 200 times 10 to the minus 6. So that's 1.2 times 10 to the minus 4 Weber. Should be pretty straightforward, that one. So look at the next thing then. Magnetic flux linkage, or N-phi. So the equation, flux linkage is equal to BAN. So it's the magnetic flux density or field strength multiplied by the area multiplied by the number of coils. So in this one, say what they're measuring. So N is just turns. A is obviously meters squared. B is Tesla or Weber per meter square. And the flux linkage, nth I, is Weber turns. That seems a strange unit, but that's definitely the unit. So be careful that we, if we calculate this, we write this correctly. So Weber turns. Let's move on. So nice and straightforward, first of all. Let's pause and have a go. A coil in a region of space has a magnetic flux density of 0.45 Tesla and a cross-sectional area of 300 centimeters squared. The coil has 250 turns. Calculate the flux linkage, or the maximum flux linkage. So we're going to use the flux linkage equals BAN. So we've got some numbers. So B is 0.45 multiplied by the area. So it's 300 centimeters squared, so that'll be 300 centimeters, or 300 times 10 to the minus 2. And then square it, so do that again. So that'll be 300 times 10 to the minus 4. Multiplied by the number of coils, which is 250. And if you put that in your calculator, you'll get an answer for the flux linkage of 3.375 Weber turns. Hopefully that went okay. Right, let's move on. Let's do an exam style question. So you have to pause and have a go at this one, and then I'll take you through the answers. A rectangular coil measuring 20mm by 35mm and having 650 turns is rotating about a horizontal axis which is at right angles to a uniform magnetic field of flux density 2.5 times 10 to the minus 3 Tesla. Plane of the coil makes an angle theta with the vertical as shown in the diagram. State the value of theta when the magnetic flux through the coil is a minimum. So the magnetic flux through the coil will be a minimum when the coil is pointing in the same direction as the magnetic field, so when it will be horizontal, so in this orientation. So the angle for that to occur will be 90 degrees. Next one, part B, calculate the magnetic flux passing through the coil when theta is 30 degrees. So what we need is the component that is perpendicular. So this component, so if that's 30 degrees, that will be cos 30. So flux is equal to BA cos theta. So we just need to put the numbers in. So it's 2.5 times 10 to the minus 3. Try and do this with enough room. Multiplied by the area, so that would be 20 times 10 to the minus 3 multiplied by 35 times 10 to the minus 3. I'm just going to write it as 20mm, but make sure that you do times 10 to the minus 3. And the same, the 35mm, so 35 times 10 to the minus 3. And then multiply that by cos 30 to get the component that is perpendicular to the magnetic field direction. And that will give us an answer of 1.52 times 10 to the minus 6 Weber. Hopefully that went okay. So part C, what is the maximum flux linkage? So flux linkage will be flux linkage equals BAN. So similar to last time, it's 2.5 times 10 to the minus 3 for the flux density, multiplied by the area, which will be the 20mm by 35mm. So 20 times 10 to the minus 3 times 35 times 10 to the minus 3. I'm going to call that A, just because I've not got much room. And then multiplied by the number of turns, 650 turns. And that gives an answer for the flux linkage of 1.14 times 10 to the minus 3 Weber turns. Hopefully that went okay. That lesson was helpful. If you've got any questions about anything, leave them in the comments and I'll get back to you. Thanks for watching, and I'll see you at the next one.